Morning, everybody. Hope you can hear me okay from the less sonically challenged UK. What I'd like to cover this morning is a discussion about how we should implement a general purpose software architecture on a Cortex-M microcontroller. If you've been in the designing firmware for embedded microcontrollers for any length of time, it's likely that you started on a smaller 8-bit microcontroller. And here our sort of traditional approach was to use a main while super loop, which ran all of our background code. And then any real-time code would be in a number of interrupt service routines. So this was very lightweight approach, gave us good real-time performance, but it didn't really scale very well. It meant all of our code was quite hard to reuse and also hard to maintain. So over the years, there have been a number of different approaches that have improved on this sort of bare metal approach. So things like event-driven frameworks or time-driven frameworks. But currently, one of the major general purpose framework that people use is a small real-time operating system, an RTOS. And also, since ARM introduced the Cortex-M microcontroller, they've spent a lot of time defining a set of standards called CMPS, the Cortex Microcontroller Software Interface Standard. And this provides a number of general purpose APIs that help us standardize the use of C code across a lot of different microcontrollers. So what I want to look at today is how we can start to use these standards to make a general purpose framework that allows us to reuse code and move code between different microcontroller families. So within the CMPS standard, there are a number of specifications that help us do this. One of the first standards that was introduced was CMPS Core. So this is a set of very low-level helper functions that allow us to talk to the registers within the Cortex microcontroller, or within the Cortex processor rather, and that's the same across all of the different Cortex processors and any different manufacturer's microcontroller. So we can use CMPS Core whenever we want to talk to the processor, and that code is then going to be portable across lots of different devices. We also recommend the use of an RTOS as well. So part of the CMPS standards includes a CMPS RTOS API, and this standardizes the calls for a small lightweight operating system, irrespective of the actual RTOS that you're using underneath. So again, this makes our code portable, not just between microcontrollers, but between operating systems as well. So we can chop and change as we need to. And then finally, to talk to the peripherals that are on the device, since these are all different between different microcontrollers, this is the most common problem that we have. But ARM also introduced CMPS driver, and this is a standard API to talk to a lot of common peripherals, mostly communication peripherals that are on microcontrollers. So this can make our code portable between lots of different devices. So within our operating system, we'll have a small real-time scheduler. This will talk to the hardware driver layer, and then we can start to build our application code as operating system threads that run the bulk of our application. So this gives us a very structured code development environment. It's approach to an object-oriented design, so we can consider each thread in isolation, design and test them. It gives us improved project management and code integration as well. The approach of using an RTOS makes our code also, as we'll see, much more portable as well. So we can go towards much better code reuse. And this is where we can get a lot of productivity gains by stop reinventing the wheel and designing our code so that it's much more easy to reuse. It's also a multi-threaded design. So again, it gives us a lot more flexibility in how we can design our operating systems. And also the use of an RTOS is a great way to integrate third-party middleware stacks as well. So as our projects get more complicated, a fact of life of using a Cortex microcontroller is that in order to actually get a project completed, much of the time you're going to have to use some third-party middleware or a library for the more advanced peripherals that are on the device. So with that in mind, we can start to think of our code as a set of objects where data is moved between them. So our threads are generally linked together by message queues, and the whole system works almost like data pumping round the system. So this gives us a higher level abstraction where we can think at the system level of our architecture and then design the functionality of the system to exist within each of our threads. So on top of this, we can start to build a general purpose framework. So this will be a layered architecture. So there's 3 user layers and then the RTOS as a standard layer. Separate from the application, we'll also increasingly need some form of second stage bootloader so that we can manage firmware updates within our system as well. So we have our main application, which sits on top of a bootloader project. So in terms of our general purpose architecture, at the top we have separate threads. So each of these perform the functionality, the design, hold the actual application code. Then in the service layer, we have our individual components. So these are essentially the library code. The bulk of our code will sit in the service layer and be called from the application threads. And then to interface with the hardware, we have a standard driver layer, which talks to all of the peripherals that we're going to use within our system. So as well as having layers, we're also functionally isolating each of our threads and components and drivers. So they're in well-defined modules that make them easy to extract, easy to test, and easy to reuse. So it's developing a discipline of how we not only write the code, but how we lay it out within our system as well, that's going to give us big gains for performance. And this is all zero cost. It just takes a bit of thinking about, and once you have a system together, it helps you improve on many fronts just by really a software specification. So here we'll have a user thread at the top. So this is running the application code, and it's making calls into a component, which will be, for example, a keyboard scanner. And then underneath this, we have separate drivers. So we might need a timer, and then we'll also need GPIO access through a new CMPS standard called CMPS Virtual I/O. So our keyboard scanner is now really just C code in a single C module that we can reuse. It provides an API to the thread code, and it uses standard driver interfaces to the hardware. So we can then wrap test code around the core module, and we can also take it out and reuse it on any other device. So comparing this over the right-hand side here in a more traditional project, generally you'll get well-written C code, but it will all be bundled into a number of probably fairly large files, and these contain a mishmash of code. So maybe thread code, maybe some of the scanner functions, maybe functions from other part of the code, and also some interrupt service routines. So it's all jumbled together. It's quite hard to test it, and it's virtually impossible to reuse it without a lot of additional work. So a good structured approach is going to give you big gains. So when we look at our thread layer, at the beginning of the project, we have to decide how many threads we want in the system, and generally we want to keep a minimum number. And the way to identify a thread is to think about the units of concurrency in the system. So the number of things that can happen in parallel, and these then become our natural threads. So we can build up a specification for each thread, how they're going to communicate together to build up the full application. So within the RTOS, there are a number of ways to communicate. You can use signals, mutexes, semaphores, but to move data around, the ideal way is using message queues, as these provide an ideal test interface, and it also makes the actual thread code easier to reuse if we want to as well. We should also specify that threads only make calls into the service layer to software components, and they don't ever access the microcontroller hardware directly, except through the CMPS core functions and also the CMPS driver functions. But ideally, they'll just be making calls to library functions that are in the service layer, or the component functions that are in the service layer. We can also, over time, develop some standard threads as well that we can reuse. So a typical one would be a supervisor thread. So this would be in charge of things like the system configuration at startup, maybe managing things like watchdogs, doing power management within the system as well. We can also use it for error handling and logging. And once this is written, we can simply reuse it and enable the bits within the supervisor thread that we want. If we're using a bootloader in the system, we probably have code to act as an update client as well, that's used to download firmware and place it into staging sectors within the flash memory. In terms of the bootloader, there is a very good open source project called MCU Boot. We did do a webinar on this earlier in the year, and if you're interested, we can send you the link to that. But this is a general purpose bootloader for 32-bit microcontrollers. It supports multiple images, also image signing and encryption. And it's also now been adopted as part of the ARM platform security architecture for IoT devices. So again, if you're looking to add a bootloader to your system, then this certainly is worth a look. And it's been ported to a number of different ARM-based microcontrollers, both by the Platform Security Architecture project and also by various silicon vendors as well. So it's becoming quite widely adopted across the industry. Now, our threads are going to make calls into our software components, and these effectively are self-contained libraries that provide a well-defined API up to the thread layer. They're all functionally isolated from each other, again, to aid reuse and testing. They'll support things like interrupts through callback functions that are located within the component, and we'll see how that works with the driver in a little bit. They should not really need to access functions that are other components, and there are only other they never access the microcontroller hardware directly, but use the driver layer to talk through to the hardware. So again, this makes them quite portable and again improves testability and documentation. So when we design our components, there's a set of software principles that was developed by Robert C. Martin in his book Clean Architecture. So these have the acronym SOLID, which we can use as a basis for our software components. So first of all, the S stands for single responsibility. So this means that our software component is really providing one area of functionality of our code. It's isolated away in its own modules and it's completely functionally isolated from every other part of the software. So this is a set of cohesive functions and data structures. We use good layout principles for easy code reuse. So typically this will provide a header file with the usage API to the thread layer, and have a separate header, which is a configuration file, which has all the hash defines that we can use to configure our component. And within the development tools, as we see in the next webinar, we can add a configuration wizard here, which makes the code much more intuitive to set up, either for a third-party user or yourself when you come back to the software after about 3 months or so and forgotten exactly how it works. There's also the open close principle, so that once we've defined a software component and created it, it should be open for extension but closed for modification. So this means we don't change the abstraction interface, but we just add new functionality to it. So this keeps our component backwards compatible for any previous projects that we've done. Um, Also, because there should be a substitution principle, so that components within our software component can be replaced or substituted for other components. So this is typically what we're looking at the driver layer. So we have a standard driver interface, but we can swap the actual drivers around to support different microcontrollers. So again, our software component is completely abstracted away from the hardware. We should also, if our component's fairly complex, we can provide different interface headers to support different aspects of our software component. So this means that different threads might use different headers, or if there's one area of the library that we're not using, then we don't have to actually build or include all of that code. So our component can be quite modular as well, to minimize its footprint over a number of different projects. So again, if we think about that when we're designing it, we can switch on and off areas of code through our configuration file to remove redundancies, or even use the compiler to remove dead code from the component. We should have a dependency inversion principle as well, so that we have abstraction functions that will always stay the same, even if we modify the component or the driver. So this makes the actual thread code not dependent on any low-level details. So we can write the business logic fairly freely, and then allow the component and the driver to worry about the implementation details. So this keeps our high-level application code fairly clean, and it doesn't get compromised by anything that we've done lower down the chain. So our software component will be a set of functions, a clean interface to the thread code, a modified configuration wizard, and a nice abstraction interface so that we can build our thread code very easy. Around this, we can design our software component in a separate sub project, so that we can develop it in isolation, build a test harness around it, and then when we're happy, we can start to integrate our components together. So this gives us a slightly different approach to developing code that we might be used to, and we'll have a look at that in the next webinar as well. We can also make our components intelligent as well by adding their own dedicated threads. So as well as just being a library of functions, we can have an active thread within the component, so that when we start up or initialize the component, it creates its own runtime thread that runs in addition to our standard application threads. So here, this might be a communication stack or something similar. Within the operating system, we can set up our threads so that they allocate their own memory from free memory as well, rather than the RTOS memory pool. So this is quite a good trick when we're building software components, so that if the thread and the code compiles, then all the memory necessary for the project has been allocated. So we know that then the component should run successfully in our project. So we have, again, a standard set of files, so that once we start to create this system, people that become familiar with it can navigate our code nice and quickly. So we have a component.c file, a configuration file, header files, and header configuration files. So we can also place user-defined functions that we might need to overload into this component configuration.c file. So it'll be a common place to look for anything that we might need to modify for a specific project. Sorry. Now on the driver layer, we need to have a standard API to talk to the common peripherals that are on microcontrollers. And this is really what CMSIS driver was developed for. Initially, it was to provide a standard API for third-party middleware so that people wouldn't have to continually be doing lots of different ports to different microcontrollers. So we can take advantage of this to use the CMSIS drivers to interface to whatever hardware we happen to have underneath. There's nothing to stop you writing a specific driver if you need features of a peripheral that are unique to a given microcontroller. And that allows us to get the best performance out of the microcontroller whilst using standard drivers for less critical areas of the code. So currently CMSIS driver supports a wide range of peripherals on the microcontroller. Typically, these are communication peripherals. Again, this was developed largely for third-party middleware, typically a lot of communication type stacks, TCP/IP stacks, etc. More recently, there's a new driver called CMSIS VIO, Virtual I/O. So this allows us to nominate a number of GPIO pins, which we can then use as virtual I/O. So we can write components for things like keyboard scanner, LED control, or other front panel stuff, and then talk to that as virtual I/O, so that when we come to our new hardware, we can retarget the virtual I/O to the specific GPIO pins that we want to use. Since there's also a number of peripherals that we may want to use that are not supported by CMSIS driver, we can extend this range within our own system, so privately, and we can create a number of custom CMSIS drivers to handle things like ADC, timers, DACs, etc. So this is some work that we'd have to do, but once we've defined these profiles and created some templates for the drivers, the actual overhead of developing the CMSIS driver is really quite low. And again, as we'll see, there's a standard test framework. So once we've created the drivers, we have a standard way of testing them to prove them out on our hardware. And this really does work as a very good board bring-up system as well at the early stages of a project. But again, we'll look at custom drivers next week. Next week. So the CMSIS API itself is pretty standard across all of the devices. So we have an initialize function that will install the callback function that's part of our component. It will also switch on the device and configure any GPIO that we need as well. We can then use the control function to fully configure the peripheral for our settings. And then through control, we can also send and receive data as well. Depending on the CMSIS driver, there may be a number of specific custom functions to cope with the peripheral that we're using. So we can mimic this API and extend that for the hardware peripherals that we're likely to use that aren't covered. Now, the CMSIS drivers are intended as quite lightweight frameworks, and generally they are code only within the driver, that there isn't any actual data usage. So this means we can instantiate multiple drivers using the same base code. So once you've done a CMSIS driver, say for a UART or a timer, we can then run it on any timer or UART that's within the microcontroller. This, as a standard API, is quite easy to provide mocking code for testing. Once we've provided those mocks and test functions, the beauty is you only need to do it once, and then we can use it across all our future projects. So again, some effort during the startup phase, but then we reap the benefits later on. Jam tomorrow. So once we've developed our software components, we'll be able to reuse them in future projects, provided we have the range of CMPS drivers that we need. So this, in future projects, then this will give us lots of time saving because the component is device and project independent. We've already documented it. We have existing test harnesses that we can run straight away. And once we've developed it, we're also able to characterize it as well. So this means we'll know its code size, its RAM size. Using the debugger, we can get some execution benchmarks so we can see its various runtime. We know what CMPS driver resources it's going to need. And also using the development tools, we can see, if we need to, we can see its power requirements as well. So we can get an idea of how energy hungry it is. So this means at the early stage of a project, if we're reusing a number of components, it will give us an idea of the code size, RAM size, and also the performance level that we need from the CPU. So this gives us a good guide for also then selecting our microcontroller as well. When we are at the requirement stage, we now have a model where we can take our requirements and break those down, decompose them into our software architecture. So we can look at the requirements, we can identify the units of concurrency, what are going to be our threads, and that will drop out as the natural parts of our system. We can see the functional requirements, so we can work out what our software components are going to be. And then that will also give us the CMPS drivers that we're going to need to build the system as well. And as I said, if we have a number of characterized components and drivers, we can work out the overall budget for our system to help with device selection. So this gives us, as I say, a good way to do design synthesis because we have a model that we've got ready built rather than thinking from scratch. So next week, we're going to look at how we can implement this software architecture using some of the features that are within the Keil MDK. So as I mentioned, within the code, we can add configuration wizards that make the software much more intuitive to use. Within the debugger, we can add component viewers, event recorders that will act sort of like plugins to the debugger to give us a much deeper view of our component and also how it's performing in real time in our code as well. We can improve our software quality. So we can spend a little bit of extra time on the component because we're going to reuse it. And we can use things like static analysis and developer test frameworks to improve the software quality. And the trick to using all this is to create a number of sub-projects so that we can bring up and test all of our components in isolation before integrating them. Once we have a software component, we can reuse it and we can then add that component to a software pack so that it can be fully integrated into the tool chain and be ready to use for developers just through selecting it through the runtime environment within the Keil Keil IDE. So we're going to have a look at that all next week. So that'll be Wednesday the 12th. So hopefully today's been useful. We are working on writing all of this down. So in the next few months, ideally, there'll be a tutorial and specification that you'll be able to have a look at in more detail. So again, if that's of interest, let us know. And hope to see you all next week where we can look at the implementation details.